Okay, here's chapter 19, homework number 1. We start off with a simple pendulum that consists of a bob attached to a cord that oscillates in a vertical plane. And we're supposed to determine the amplitude of the motion in degrees and the maximum tangential acceleration of the bob. So we know that omega n, or the natural frequency, is 2 pi over tau, or the period. So we know that omega n is equal to 2 pi over 1.3, which is 4.833 radians per second. Similarly, we know that theta is equal to theta m sine omega n t plus phi. Knowing that, if we take the derivative of theta with respect to time, we get what simplifies out to be theta dot is equal to theta m omega n cosine omega n t plus phi. And then if we take it one step further and take the derivative of theta dot with respect to time, we get is equal to 0. So using all that, we can confirm that 0 is equal to omega nt plus phi. And since omega nt plus phi is 0, theta dot becomes equal to omega n times theta m. And we know that Vm is equal to L times theta dot m. Along with that, we know the natural frequency is equal to the square root of g over L. We can solve for L there, which is 0.42 meters, and then combining those two, and really those three, we can solve for theta, which would end up to be 0.197 radians, or 11.3 degrees. And if we we know that theta double dot is equal to theta m omega n squared, and that acceleration is equal to length times omega double dot. We know theta double dot is theta m times omega squared. So we can plug in all our knowns there and get 1.93 meters per second squared for the acceleration. Number 2, we have two springs of constant K1 and K2, and they are connected in series to block A that vibrates in a simple harmonic motion with a period of 5 seconds. When the same two springs are connected in parallel to the same block, the block vibrates with a period of 2 seconds. We're supposed to determine the ratio K1 over K2. So we know K in series is K1 times K2 over K1 plus K2. We know K in parallel is equal to K1 plus K2. We know the period in series is 2 pi over the square root of Kg over m, and the period in parallel is 2 pi over the square root of Kp over m. If we take the series period over the parallel period, we'll end up with that is equal to the square root of Kp over K. We know that what the series period is and the parallel period is 5 over 2. And we can use that to continually to simplify. And we'll go on eventually to get to a point where we use the quadratic formula to solve for what the ratio K1 over K2 should be, and it turns out to be 4. Number 3, we have a 40 millimeter deflection on the second floor of a building. It's measured directly under a newly installed 3,500 kilogram piece of rotating machinery with a slightly unbalanced motor. And we're supposed to determine the equivalent spring constant of the floor system and the speed and RPM of the rotating machinery that should be avoided if it is not to coincide with the natural frequency of the floor machinery system. So if we just take the sum of the forces, we get mg is equal to k delta, and if we solve for k there, we get K is equal to mg over delta, which is 858,375 newtons per meter. And then we know that the natural frequency is equal to the square root of K over m. So we can solve for the natural frequency, which is 15.66 radians per second, or 149.5 revolutions per minute. Number 4. We have a 6 kilogram uniform cylinder that is connected at a pin to a 4 kilogram horizontal bar, which is connected on either side to a spring with a constant of 5 Newton meters, and is moved 12 millimeters to the right of equilibrium and let go, and is let go of. And we're supposed to determine the period of vibration for the system and the magnitude of the maximum velocity of the bar AB. So we can go ahead and draw a free body diagram of the system. And we will realize that x is equal to r theta and a is equal to r alpha. And if we sum the forces in the x direction, we will get negative 2 kx minus f is equal to mb plus mc times a. And if we take the moment about c, we get fr is equal to ic alpha, which if you plug in ic and solve for f, it becomes f is equal to mcr over 2 times alpha. And then since, like we already knew, r alpha is equal to a, we can go ahead and simplify that equation down to a is equal to negative 4kx over 2 mb plus 3mc. And then we know that a is equal to negative omega n squared times x. If we go ahead, plug that in, plug in our unknowns there, we get Wn is equal to the square root of 4k over 2mb plus 3mc. And then knowing that the period is equal to 2 pi over natural frequency, we can go ahead, plug in all our knowns, and get 2.265 seconds for the period. And we know that Vmax is equal to A times omega n, which would turn to be 2 pi times A over the period, which is 2 pi times 0.012 divided by 0.2265, which will give us 0.3328 meters per second. Number 5, we have a uniform disc, and it's welded at its center to 2 elastic rods of equal length. We're supposed to determine the mass of the disc and the period of vibration if one of the rods is removed. So, first of all, we know that, first we'll draw a free body diagram of the system, and then we'll get that K is equal to T over theta. And if we plug in our knowns there, we get K is equal to 3.58 Newton meters per radian. If we sum the moment, we get negative K theta is equal to J double dot theta double dot. And we know that omega n is equal to the square root of K over J. Along with that, we know that tau n is equal to 2 pi over omega n. Combining those, we get J is equal to 3.58 times 1.3 squared over 2 pi squared, which is 1.533 Newton meter second squared. We also know that J is equal to 1/2 mr squared, so we can use that to solve for the mass, which is 21.29 kilograms. And if we remove a rod, then the new constant becomes half of the old constant, which is just 1.79 Newton meter per radian. And then similarly, we know that omega n is equal to the square root of K over J. We can plug in our knowns there. And then similarly, we know the period is 2 pi over the natural frequency, so we can just solve for the period there as well. And it's 1.835 seconds if one of the rods is removed. Number 6, we have a 15-pound uniform cylinder that can roll without sliding on an incline and is attached to a spring AB. If the center of the cylinder is moved 0.4 inches down the incline and released, determine the period of vibration and the maximum velocity of the center of the cylinder. So here we know that T1 is equal to 0. We know that V1 is equal to 1/2 K times delta plus R theta M squared. We know T2 is equal to 1/2 J theta dot squared plus 1/2 MV squared. We know that V2 is MGH plus 1/2 K delta squared. And we know that T1 plus V1 is equal to T2 plus V2. We can go ahead and plug in all our knowns there, and we will get what simplifies down to be 2K delta R theta plus K R squared theta squared is equal to J theta dot squared plus MV squared plus 2MGH. Now, we can keep that for later and take the moment about C, which is equal to 0. And so we'll get these two equations from that. Well, we get that first equation, but we know that the height is equal to R sine beta times theta M. So we can combine those two and get MGH is equal to K delta R theta. And then combining that with the equation above, we can get what simplifies out to be K R squared theta squared is equal to J theta dot squared plus MV squared. And we know that theta dot is equal to omega times theta. And we know that Vm is equal to R theta dot. And combining those, we get Vm is equal to R omega theta. And using that with the equation above, we can get what simplifies down to be omega n squared is equal to K R squared over J plus Mr squared. And we also know that J is equal to 1/2 Mr squared. So using that and combining, we can get omega n squared is equal to 2K over 3M. Now, using the period is equal to 2 pi over the natural frequency, we can solve for the period, which is 0.715 seconds. And we can also use the equation that was given just a couple steps before to solve for the velocity, which is 0.293 feet per second. All right, number 7. We have a 20-pound rod AB attached to two 8-pound discs, and knowing that the discs roll without sliding, we're supposed to determine the frequency of small oscillations of the system. So, first of all, we know that V is equal to R omega. Using that, we get Vm is equal to 1/2 omega m, and Vab is 1/6 omega m. After that, we know that T1 is equal to 0. We know that V1 is equal to negative 1/3 WAD cosine theta. We know that T2 is equal to 2 times 1/2 MV squared plus 1/2 I omega squared plus 1/2 MAB VAB squared. And then plugging in our knowns there, we can simplify that whole thing down to 3.2778 omega squared G. And then after that, we can find V2, which is negative 1/3 WAB. After that, we know that T1 plus V1 is equal to T2 plus V2, so we can go ahead and plug in all our knowns there. After we plug in our knowns, we get 1 minus cosine theta m in that equation after we solve. So we'll have to use 1 minus cosine theta m is equal to 1/2 theta squared, since we're looking for small oscillations of the system. So if we plug in our knowns, and we know that omega m is equal to theta m times omega, if we plug in our knowns, we should be able to solve for omega, which is 5.722 radians per second. And the frequency should be omega over 2 pi, which is just 0.91 hertz. 0.911 hertz. Um, 8. We have a section of uniform pipe that is suspended from 2 vertical cables attached at A and B. We're supposed to determine the frequency of oscillation when the pipe is given a small rotation about the centroidal axis and released. So we can go ahead and draw a free body diagram of what's going on in the system. Here we find that A times A2 is equal to B times B2 is equal to A over 2 times theta m is equal to L times alpha. And we know that alpha is equal to A over 2L times theta m. And we also know the inertia is ma squared over 12. And we know that theta dot is equal to omega n theta m. Knowing that and that T1 is equal to 1/2 I theta dot m squared, we can go ahead and combine those last 3 equations and get T1 that is equal to 1/2 ma squared over 12 omega n theta m squared. We also know that V1 is equal to 0, T2 is equal to 0. V2 is equal to mg yc. In this case, yc is L times 1 minus cosine alpha. For small angles, the whole V2, the whole thing simplifies down to be mgl times a squared over 8l squared theta squared. Knowing that T1 plus V1 is equal to T2 plus V2, we can go ahead and plug in all our knowns, which will simplify down to omega n squared is equal to 3g over L. And we know that F is equal to omega over 2 pi. So our frequency should be 1 over 2 pi times the square root of 3g over L. Number 9. We have a simple pendulum of length L, which is forced to move horizontally in relation to xc is equal to delta m sine omega f t. And we're supposed to determine the range of values for omega f in which the amplitude of the motion of the bob is less than delta m. So first of all, the steady state response xm is equal to delta m over 1 minus omega f over omega n squared. Knowing that, and knowing that negative xm is less than delta m, we can go ahead, plug xm into that, or plug the xm for xm into that, and we can keep simplifying it down. Eventually we'll get omega f is greater than the square root of 2 omega n. And we know that omega n is equal to the square root of g over L. So we can go ahead and combine that into the equation and get omega f is greater than the square root of g, the square root of 2g over L. Number 10, we have a 4 kilogram block A that's dropped from a height of 80 millimeters onto a 9 kilogram block B, which is at rest, and block B is supported by a spring constant of 1,500 Newton meters. It's attached to a dashpot of damping coefficient 230 Newton second meters. Knowing there is no rebound, determine the maximum distance the blocks will move after the impact. So first of all, we know that VA is equal to the square root of 2GH. We can plug in our knowns there. So for VA, which is 3.962 meters per second, we know that MA times VA plus MB times VB is equal to MA plus MB times V prime. Using that, we can solve for V prime. V prime is 1.219 meters per second. Static deflection is equal to negative ma g over k. We can go ahead and plug in our knowns there, and we get negative 0.02619 meters. We can solve for the critical dampening coefficient, which is equal to the square root, or 2 times the square root of Km. We can solve for that, which will give us 279.3 Newton seconds per meter. Knowing that C is less than the critical damping coefficient, we have the light damping of amplitude equation, which is x is equal to e to the negative c over 2m times c1 sine omega naught t plus c1 cosine omega naught t. We'll save that, and we'll get c over 2m is equal to 230 over 2 times 13, which is 8.846. We know that omega naught squared is equal to k over m minus c over 2m squared. We know all of those, so we can go ahead and plug in and solve for what omega naught is, which is 6.094 radians per second. We want to solve for C2, so we can go ahead and plug in to our light dampening amplitude equation, solve for C2, and get negative 0.02619 for C2. We'll have to take the derivative of that equation in order to solve for C1, which we can do. After we do that, we still have to solve for time because we haven't quite gotten everything we needed. So we'll have to go back, and at max deflection, we know that x dot is equal to v is equal to 0. So using that, we can go ahead and equate the earlier equation to 0. Go ahead and plug in everything we know. Simplify. And after we go ahead and simplify that, we can use some trigonomic relations and get our time, which should be 1.253 seconds. After we get our time, we have everything we need to go ahead and plug it into the equation fully. We'll go ahead and do that, and we get 0.0307 meters. And the total deflection is equal to the static deflection plus the other deflection. The maximum deflection is static deflection plus xm, which we have both now, so we can just add them together, which is 0.02619 plus 0.0307, which is equal to 0.0569 meters.